Have you ever looked up at the night sky and noticed those tiny moving lights? Many aren't stars. They're satellites, our tireless helpers in space. They guide GPS, bring us TV, and help forecast the weather by watching clouds and storms from above. Satellites also let us call family far away and even explore the universe, snapping photos of distant galaxies. Today, anyone can join this adventure. Students and hobbyists build small satellites called CubeSats to run experiments or send messages from space. Ready to build your own friend in the sky? Every satellite, big or small, is built from 4 main parts: structure, power, communication, and payload. The structure is the frame, strong but light, often a simple metal cube for CubeSats. Power comes from solar panels and batteries, keeping the satellite running day and night. The communication system is its mouth and ears, using antennas to send data to Earth and receive commands. The payload is the mission's heart, maybe a camera, a sensor, or even a speaker. Each part works together, turning a box of parts into a space explorer. That's the magic of satellite design. Every satellite mission, no matter how big or small, always begins with a plan. Before anything is built or launched, a team of engineers and scientists gathers to brainstorm, sketch, and imagine what their satellite could achieve. This is the foundation of every successful space project. The first question is simple, but crucial. What do you want your satellite to do? Is it meant to take breathtaking images of Earth, monitor weather patterns, track ships at sea, or perhaps test a new technology in orbit? The possibilities are endless, but you need a clear purpose to guide every decision that follows. Define your mission objectives in detail. Will your satellite take high-resolution photos, measure temperatures in the atmosphere, detect radiation, or relay messages between distant locations? Each goal shapes the design and capabilities of your spacecraft. Maybe your mission is to send a message from orbit, or to collect scientific data and beam it back to Earth. Whatever the task, clarity at this stage is essential. Next, sketch your satellite's design. Think of it as a complex puzzle. Structure, power systems, communication antennas, and the payload all need to fit together seamlessly. Each component must work in harmony, and every detail matters. Create a detailed power budget. List every part's energy needs, from cameras and sensors to computers and radios. This step ensures your satellite won't run out of power in the harsh environment of space. Then, size your solar panels and batteries to match those needs. The right balance keeps your satellite running day and night, through sunlight and shadow. Choose your orbit carefully. Most CubeSats and small satellites are launched into low Earth orbit, or LEO, circling the planet just a few hundred kilometers above the surface. Your orbit determines how your satellite moves, what it can observe, and how often it can communicate with the ground. The orbit you select affects what your satellite can see, whether it's scanning the same spot every day or covering the entire globe over time. It also determines how often your satellite passes overhead, and when you can send or receive data. Timing is everything in space missions. Sometimes, you won't get to pick your exact orbit, especially if you're sharing a rocket with other satellites. But understanding your orbit's details is key to planning your mission and making the most of every opportunity. Mastering these details early helps you avoid costly mistakes and ensures your satellite will do what you need it to do once it's in space. Careful, thorough planning now means fewer surprises and smoother operations later. Every checklist, every calculation, and every discussion brings you one step closer to launch. That's how real space missions begin, with a big plan, a dedicated team, and a vision for what's possible beyond our world. With your plan ready, it's time to gather parts and tools. Think of it as a space treasure hunt. Most beginners use commercial off-the-shelf, COTS parts, CubeSat frames, solar panels, batteries, radios, and a flight computer. Your payload could be a camera, sensor, or experiment, whatever fits your mission. You'll need basic tools, soldering iron, multimeter, wire strippers, screwdrivers, and an anti-static wrist strap. Set up a clean, organized workspace. Dust and clutter can ruin delicate electronics. Professional clean rooms aren't required, but tidy habits are a must. Every part and tool has a purpose. Choose wisely. Now you're ready to build. Assembly time. Start by mounting solar panels on the CubeSat frame, then install deployment switches that wake the satellite once in space. Slide in the power board and flight computer, connecting them to batteries and solar panels. Fit check everything before final assembly. Organization is key. Add your payload and communication system, making sure cameras or sensors have a clear view. Connect everything with cables, linking the payload, computer, and radio. Take photos and label cables as you go. Documentation helps with troubleshooting. Double check for pinched wires, then close up the satellite. Now you're holding a real spacecraft ready for its journey. It's a moment to remember. Think of hardware as the body of your satellite, the physical structure and components that make up its form. But it's the software, the code you write, that acts as the mind, giving your satellite intelligence, purpose, and the ability to interact with its environment. Without software, even the most advanced hardware is lifeless, unable to perform any meaningful task. It's your code that breathes life into the satellite, transforming it from a static object into a dynamic, responsive machine capable of complex operations in the harsh environment of space. Every line of code you write is a set of instructions, telling the satellite exactly how to behave. From the moment you upload your software, your satellite becomes an active participant in its mission, ready to respond to commands and carry out its objectives. Start by writing the boot-up sequence. When the deployment switches are released after launch, your code tells the satellite to pause, check its status, and then carefully deploy its antenna. Once the antenna is out, the satellite sends a beacon signal back to Earth, letting you know it's alive and functioning. Next, program the satellite to constantly monitor its vital signs: battery voltage, temperature, and other critical parameters. If anything goes wrong, your software should automatically put the satellite into safe mode, protecting it from damage and preserving its mission. The heart of your mission lies in the payload. Write code that tells the payload when to activate, how to collect scientific data, and where to store that information in memory. Your software ensures that every experiment runs smoothly and that no valuable data is lost. Communication is key. Program the radio system to listen for commands from ground control, interpret them, and respond appropriately. Whether it's a request to take a picture, transmit data, or adjust settings, your code makes real-time interaction possible. For example, when ground control sends a command like "take a picture" or "send data," your software must recognize the instruction, execute the task, and confirm completion by sending a response back to Earth. Debugging is an essential part of the process. Add print statements throughout your code to track what's happening at each step. These messages help you catch errors, understand the satellite's behavior, and ensure everything works as intended. Test your code in every possible scenario, both in simulation and on real hardware. In space, there's no room for mistakes. Robust, reliable software is absolutely essential. It must handle unexpected situations gracefully and keep the satellite operating smoothly, even when things don't go as planned. Ultimately, the success of your satellite mission depends on the quality of your code. With careful programming, thorough testing, and attention to detail, your satellite can achieve its goals and make a real impact in space exploration. Problems are part of the journey. Don't panic. If the satellite won't power on, use your multimeter to trace electricity and check connections. Debugging software? Add print statements to track what the code is doing and find where things go wrong. Mechanical issues like short cables or tight fits may need creative fixes. Reroute wires or adjust non-critical parts. Fit checks and documentation help prevent surprises, but every challenge is a learning opportunity. Solving problems builds your skills and confidence. Each fix makes your satellite stronger. Even NASA faces setbacks. What matters is how you respond. Every solved problem is a victory. Before launch, your satellite must pass tough tests to prove it's space-ready. Run a day-in-the-life test. Simulate sunlight and darkness to check power and software. Shake tests mimic rocket vibrations. Nothing should break or come loose. Thermal vacuum tests expose the satellite to extreme temperatures and vacuum, just like space. Outgassing removes trapped air or chemicals that could cause trouble in orbit. Test communications, send commands, and receive data from your ground station. Passing these tests means your satellite is flight-ready. It's a huge milestone. Celebrate your hard work. The final step: launch. After months, sometimes years, of planning, designing, and building, everything comes down to this electrifying moment. The rocket stands tall on the launch pad, engines rumbling as the countdown begins. Every second is filled with anticipation and hope as your team gathers to witness the culmination of your hard work. Most CubeSats hitch a ride as secondary payloads on big rockets. These small satellites are carefully packed alongside larger missions, sharing the journey to space. This approach makes space more accessible, allowing universities, research groups, and even high school teams to send their experiments into orbit without the massive costs of a dedicated launch. You'll apply for a launch slot, then hand over your satellite for integration. In a pristine, clean room, engineers meticulously check every connection and system, ensuring your CubeSat is ready for the harsh environment of space. The handoff is both exciting and nerve-wracking. Your creation is now in the hands of the launch team. On launch day, watch as your creation blasts off, carrying your dream into space. The roar of engines, the trail of fire, and the sight of the rocket disappearing into the sky is unforgettable. For many, it's a lifelong dream realized in a matter of minutes. After launch, the waiting begins at your ground station. Operators sit at their computers, eyes glued to screens, antennas pointed skyward, listening for the first signal. A beacon that says your satellite survived the journey and is alive in orbit. That first beep is pure joy, a message from something you built, now orbiting Earth. It's proof that your hard work paid off, and your satellite is ready to begin its mission. The team erupts in celebration, knowing they've achieved something extraordinary. Building a satellite is more than engineering. It's about curiosity, creativity, and reaching for the stars. It's a journey that brings together people from all backgrounds, united by a shared passion for discovery and innovation. Every challenge overcome is a lesson learned, and every success is a step closer to the future. Space is for everyone: students, hobbyists, dreamers. No matter your age or background, the universe is open to those who dare to imagine and work to make their vision a reality. The night sky inspires us all to dream bigger and reach higher. Your satellite is a tiny ambassador, inspiring the next generation to look up and explore. It's a symbol of what's possible when imagination meets determination, and a reminder that the journey to space begins with a single dream: